because it is all about word problems, and sometimes it gets kind of annoying writing out all these words. So this is our basic formula for any exponential growth or decay. The a sub 0 is going to be your initial value. And k is going to be your growth rate. So we have a situation, in 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. And we want to find a function that models this data from 1970 to 2010. So since we're starting in 1970, then this is my initial value. Oh, that should be a t. This is with time. So f of t is going to equal the initial value times e to the kt. Now, k is something we want to find. We want to know the growth rate. So do we know another time and another population value? Well, we do. In 2010, the population is 308.7. So what t value is that? So if we're talking about years, how many years from 1970 to 2010? Well, that would be t equals 40. So I need to fill in that data so I can find my growth rate. So I'm solving for k. So the first thing you're going to want to do is divide both sides by that leading coefficient. And so I've got 308.7 divided by 203.3. And that's 1.518 equals e to the, and I'm going to write that as 40k because it just makes it a little bit easier. Now, if you think back on solving the equations, if I have e to some exponent equals a number, and I want to get that exponent out, I'm going to rewrite this. Rewrite as a log. So the exponent will equal the log base e of 1.518. Well, log base e is log. That doesn't make sense. That's actually ln. Which is in any calculator. And then I'm going to take that divided by that 40. And I get k is 0.0104. You probably want to go as many decimal places as you can. So my new equation is 203.3 e to the 0.0104t. So when will the U.S. population reach 335 million? So now we're wanting to know the time when f of t gets to 335 million. So the first thing I would do is divide by the 203.3. I'm just going to go 6478. That's fine. Equals e to the 0.0104t. To get the exponent out, we're going to rewrite it. Log base e is natural log. So natural log of 1.6478. Then I'm going to be dividing by that coefficient. Whoops, I put too many decimal places. I don't know what I was doing there. And so t equals 48.02. But since we're talking about years, I'm okay with that. But what year is that? So if we started in 1970, add 48 to it, that would have been 2018. Half-life is the time it takes for half of a substance to disintegrate. Carbon-14 has a half-life of 5715 years. Find an exponential decay model. So what that means is in this amount of time, we will have half of our value left. So in other words, if we started with 100, it'll reach 50 in K times 5715. Half of the amount is left in that many years. Well, I need to solve for K. Same process. So I'm going to divide by 100. That's going to give me a 1/2 equals e to the 5715K. 5715K equals natural log of 1/2. Natural log of 1/2 divided by 5715 gives me -1. Okay, so let me write this out. -1.213 e to the -4. So let's talk about what this e, I should have wrote it this way, really means. That's 10 to the -4th. So my k is actually -0.001213. It's a very, very small number. But that's okay. Now I'm putting a sub 0 because we don't know what the initial amount is. Somebody would have to know that and then plug into there, and you'd be able to find the date. And we'll do that right here. So in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found. They found that the scroll wrappings contained 76% of their original carbon. So notice here, we're talking about a half-life. This ended up just being a half, right? So I'm going to take 0.76 would be, if I took the future value divided by the original value, would be 0.76, 76%. E to the -0.001213 T. And I'm going to find out how old estimate the age of them, how long ago that they were found. So I'm going to need to do a natural log of 0.76, then divide that by the -0.001213. And it says that the time is 2,000 years old. Last example. We're given a function, and this describes the number of people who've become ill with the flu, oh my God, so many number of weeks after its initial outbreak in a town with 30,000 inhabitants. How many people became ill with the flu when the epidemic began? So when it began, that's at t equals 0. So what I'm going to do with this one is, since I do have a graphing calculator, and you could do this in Desmos as well, is I'm going to actually put the equation in, and then I'm going to go to the table. You can do the same thing with Desmos. And I'm going to look at the table. So it says at the beginning, at time equals 0, 1,429 people were sick. In 4 weeks, we are up to 28,583 people. What is the limiting size of the function? In other words, is there an amount that it limits out at? And you'll see here, oh, it doesn't go any higher than 30,000. Why is that? The town has 30,000 people. That's the limit. Notice in the equation, 30,000 is in the top. That's another way you can find that limiting size.